And so this is an energy level diagram for hydrogen, and it's showing, for example, if the hydrogen starts in the ground state, level 2 is 10.2 electron volts above that, level 3 is 12.1 electron volts above that, and so forth. So a hydrogen atom in the ground state can't accept a photon with 5 electron volts, not enough to get to level 2. Can't accept an electron with 11 electron volts because it's more than enough to get to level 2, but not enough to get to level 3. If it's exactly 10.2 electron volts, bingo, that's just right to go from the ground state to level 2, because that takes 10.2 electron volts. Also, once the atom has its electron in the level of 10.2 electron volts, the electron can drop back down to the ground state and give up 10.2 electron volts. So let me ask you this. Suppose the electron was in level 2 to begin with, and a photon comes along with 0.7 electron volts of energy. If the electron starts in level 2, could it absorb a photon with 0.7 electron volts? No, because that's not enough to get up to level 3. What is enough to get to level 3? How many eV does it take to get to level 3 if you're starting on level 2? Tell me the number you have to, the two numbers you have to subtract. What minus what? 12.1 and 10.2. So 12.1 minus 10.2 is 1.9. So if a photon comes along with 1.8 electron volts, what happens? If it comes along with 1.9 electron volts, what can happen? It can jump up to level 2. What if it's got 2 electron volts? Because that would be too much for level to go to level 3, not enough to get to 4. But 1.9 electron volts could take the electron in level 2 right up to level 3. What if I had 2.6 electron volts? 2.6 electron volts. What is 12.8 minus 10.2? 2.6. I'm going to ask you again, what if I had 2.6 eV photon come along? It could jump up to level 4. It could jump up 2 levels, and so forth. As long as the photon has just the right amount of energy to take you from whatever level you're in up to some higher energy level, you can absorb it. Other than that, it's just going to ignore it. And for emission, it will spontaneously drop to some lower energy level. So if the photon started in level 4, it could, if the electron, not the photon, if the electron started in level 4, it could give up 0.7 electron volts of energy to create a photon with that energy and drop down to level 3. Or it could give up 2.6 electron volts of energy and drop down from level 4 all the way down to level 2. Or it could give up 12.8 electron volts of energy and go all the way from level 4 down to level 1, the ground state. So an atom can emit and absorb photons with energies equal to differences in energies of pairs of levels that the electron is able to be in, pairs of energy levels. Do you have a question?
Yes. So what? So how are they related to the spectrum?
So the idea is, we're not going to see one photon from one atom. That's not enough.
Right.
But on the other hand, if I have a whole gas of atoms, say, like, here we're doing a light bulb. Here's this whole gas of this imaginary 2-level atom that only is able to emit or absorb this particular green wavelength in this case. Got a whole gas of these atoms in front of this light bulb. The light bulb filament is giving off a continuous spectrum, all the colors of the rainbow, and most of them go right through the gas because those atoms ignore everything but that particular green wavelength that they're good at absorbing. And so if you have the light pass through the gas and then into a spectrometer where you've got a slit and a prism to spread the light out, then there will be light missing at that particular wavelength that the atoms are good at absorbing, but all the other light gets through, and so you will see an absorption line at that particular wavelength because atoms are absorbing that particular wavelength out of the light coming from the light bulb. The other thing you could do is to have a hot version of that gas, say put it in a glass tube and heat it to a high temperature by passing a current through it. Did that in class all the time. Turned on these spectrum tube lamps. And then in that case, what you would see is the gas would glow, and it would glow that green color because atoms had been excited to the upper level and were dropping down to the lower level and giving off light at that wavelength. But typically what we see with stars is an absorption line spectrum because, let's see where I have it here, because the idea is, do I have it in there somewhere? There's a particular picture I sometimes show for that. I think it's actually in a different chapter that I have that slide. Probably 15. Where's chapter 15? There you are. Do I have it in there? Yeah. So the idea is that in a star, the temperature increases as you go deeper and deeper inside the star. So the outer layers of the star are at a lower temperature, and they're like a gas that's in front of a source of much brighter continuous spectrum. The lower, hotter layers of the star act like the light bulb, and atoms in the outer atmosphere of the star are able to absorb particular wavelengths of light from that rainbow of colors coming from below. And so when we look at the spectrum of a star, we see dips. We see, this is a plot. If I had a picture, I would see dark lines. Here I see dips in brightness that correspond to atoms in the star's cooler outer layers absorbing particular wavelengths that they're good at absorbing by having electrons jump up to higher energy levels of light coming from lower levels inside the star. And so the connection to spectra is that in the laboratory, we can measure the wavelengths that particular atoms are good at emitting and absorbing, and then when we see spectral lines at exactly those same wavelengths in stars, we can say, aha, that star contains those atoms, making those transitions, is what it comes down to. So that's, for a long time, people imagined, back in the 1800s, folks imagined we'd never know what stars are made of because we'll never be able to go there and get a sample of them. But no, it turns out you don't have to do that. You can look at their spectrum and figure out what it's made of. So, the light from the star tells us what it's made of. Smells good. I can smell it from here. I had a Chinese professor when Qing Shan Wu was here. She had this, I don't have this rule, but she had this rule, no food in the class because otherwise she would smell it and it would make her really hungry. So she just could not tolerate it. Yes?
How does neutralization in the classic core give rise to dispersed neutrinos?
Yeah, so neutronization is in, so remember we were talking about the formation of a neutron star is when the iron core collapses and it turns into a ball of neutrons in a tiny fraction, just a fraction of a second, it turns into a ball of neutrons via this process called neutronization. And is this 17 or 18? Either one. 17, okay, yeah. So then 18, they talk about the neutron star. 17, they talk about how it's made. So the idea is that there's a picture in there somewhere, I think. Yeah. So as the core collapses, one thing that happens is it becomes so hot that iron nuclei are broken apart into helium nuclei, and then as it continues to collapse, this is just a fraction of a second later, what happens is that under those conditions, electrons can combine with protons. They literally, the electron collides with a proton and turns it into a neutron, and it also gives off a neutrino. And that's where the tremendous burst of neutrinos comes from, because virtually every proton and electron into the stars being inside that collapsing core is turning into a neutron, and a neutrino is being given off as part of that process. And that's a lot of neutrinos, because there's a lot of protons and electrons that are being turned into neutrons there. Every one of them is associated with the neutrino that gets given off. And that's where the burst of neutrinos comes from, because neutronization, turning it into neutrons, every neutronization gives off a neutrino as part of the process. Yes?
Can you go over active galactic nuclei?
Active galactic nuclei, yes, they are now known to be associated with supermassive black holes in the centers of galaxies. And they're called active galactic nuclei because they give off a lot of radiation, as in electromagnetic radiation. And they are powered by the accretion disk around a supermassive black hole. So we are seeing ultimately radiation from the accretion disk, and or often there are jets that stream out from the poles of the accretion disk, and there is radiation that also moves along the poles of the accretion disk. And depending on the angle that we see it from, if that beam is aimed straight at us, we can see a quasar, which is the most active type, the most interesting, if you will. I guess they're all interesting, but the most impressive type of active galactic nucleus is quasars. They just look like stars, except that they are billions of light years away based on the redshift of the galaxies that contain them, and that tells us that they're actually not stars, that they're something much more energetic. And a supermassive black hole is the theoretical model. It's what would allow us to duplicate the properties of active galactic nuclei. Yes?
Did you already answer what reflection nebula was?
I did long ago, not today, if that's what
Okay,
you.
yeah.
Yeah, no, nobody asked that, right? Unless I've totally lost it. Nobody asked me that, right? I didn't talk about that, right? Yeah. Reflection nebula, what color are reflection nebulae? Blue. Yeah, they're blue. They are in the interstellar medium, and they are blue. Frankly, partly because often there are blue stars near them. Blue stars are the brightest stars, and so they're partly blue just because there's a lot of freaking blue light that's being scattered off of them. So for example, here's the Pleiades star cluster. Some of you saw it at the last observing session. Here's the Pleiades star cluster that just happens to be passing through a dust cloud. It's not really associated with the birth of the Pleiades in any way. It happens to be passing through a dust cloud. And the brightest stars in the Pleiades are these B-type stars that give off a lot of blue light, and so that in and of itself makes the light scattered off of little microscopic interstellar dust particles look blue. But there's more to it than that. It's even bluer than even though you can't tell it from the picture, the light scattering off of the dust is even bluer than the starlight itself is, because of the fact that dust particles, tiny little dust particles in the interstellar medium, are better at scattering short wavelengths than long wavelengths. So a reflection nebula is caused by interstellar dust scattering preferentially shorter wavelengths than longer wavelengths, and so visually they look bluish as a result of that. Yes.
So how is, the color related to interstellar reddening?
So interstellar reddening is the other side of the coin. In other words, when we have a reflection nebula, then it is scattering short wavelengths more than long wavelengths. And in this simple cartoon picture, the idea is here's red light and blue light coming from a star. Of course, there's every color. But the blue light is to represent short wavelengths, the red light is to represent longer wavelengths. Much more of the blue light photons are scattered than the red light photons. So if we are seeing the nebula itself, seeing the dust in the nebula, we see it as blue in color because it's scattering, those dust particles are scattering mostly blue photons our way. On the other hand, if we see an object like a star through the nebula, like the telescope is supposed to be looking at the star that's behind this reflection nebula, then more of the red light from the star makes it through the nebula than the blue light. And so the star itself, something that we see through the nebula, looks redder than it would without the nebula there.
Because the red light is getting absorbed?
No, because it's getting through, because it's not being absorbed. In other words, the red photons are not as likely to be redirected out of the beam of starlight from the star that's headed towards us. And so, we see we see the dust as blue because when we see the dust itself, we're seeing the blue light that it's scattering. But if we see something through the dust, we're seeing light that isn't being scattered, that makes it through the dust. And more of the red light makes it through the dust than the blue light. Or in other words, more longer wavelength photons make it through the dust than shorter wavelength photons. And so things that we see through the dust look redder than they would if the dust wasn't there, simply because a bigger fraction of the red photons make it through than longer wavelengths, shorter wavelength photons is what I meant to say. You're dying to ask another question about that?
Yeah.
Yes,
So,
okay.
you're saying that, like, if we were to look at the star, that the area around it would appear blue, but the star itself would be red?
Yeah, if you have, if the star is way off in the background, if it's embedded in the nebulosity, like the Pleiades is, then, and again, you can't tell just by looking at this, but if you made very precise spectrophotometric measurements of the brightness versus wavelength, the idea here is, yeah, these stars are blue, but they're even bluer than they look here because the dust is scattering some of the blue light from those stars out of our direction. And so if the star is embedded in the nebulosity, the star itself looks a little redder, and the dust looks blue because the dust is scattering light to us that would have totally missed it without the dust being there. It's redirecting light in our direction, and preferentially it's redirecting short wavelength light. If you have a star way, way off in the background, you're not going to see you're not going to see the dust itself. What you'll see is the star itself just looks redder. We had a picture here that illustrates the idea of interstellar reddening, where here are two H2 regions, two star-forming regions, and an H2 region without the effect of interstellar reddening looks pink because it glows primarily in the Balmer series spectral lines of hydrogen. There's a deep red one and a turquoise one, and two of them that could arguably be called indigo, and they mix together to form a pinkish color. So this nearby, in an astronomical sense, H2 region looks pink because we're seeing all the wavelengths of hydrogen making it to us from it. This one here looks much redder because it's further away. There's more interstellar dust between us and this more distant H2 region. And so the lovely turquoise line and the damn indigo lines, those photons pretty much aren't making it to us. Only the deep red hydrogen spectral line makes it to us from this one because of interstellar reddening, and so it looks redder literally as a result of being further away from us. and having more dust able to get rid of short wavelength photons before they can even get to us. So interstellar reddening is what happens when you see something else through the dust, whereas the dust itself looks blue because it's scattering blue light. If you see something through the dust, well, the dust is scattering blue light out of the beam, and what's left is redder as a result of that, because it's missing a lot of the blue light, a lot of the shorter wavelength light. In the sense that I was concerned about this. The advantage to doing the review session later is you're more likely to have been more complete in how much you've studied so far. But the exam's at 8:30 in the morning, so I didn't want to have it that late. So I thought, I'll do it at 5. And then I'm getting this impression, it's like, oh, I'm not sure what to ask yet because I haven't studied everything yet. I don't know, what can I do? Answer your questions, that's what I can do. Yes?
What's the difference between refracting and a reflecting telescope?
All the difference in the world, because a refracting telescope uses bending of light through glass. In other words, the main light gathering element is a lens at the front of the telescope. Whereas a reflecting telescope, what kind of object reflects light? It's called a mirror. And so a reflecting telescope used a curved mirror at the bottom of the telescope. So it's fundamentally whether you're using a lens to form, you're using a lens as the primary light gathering and focusing optical element, or if you're using a mirror as the primary light gathering and focusing element in the telescope. All large telescopes in the world are, which one? Refractors or reflectors? Reflectors for sure. Yeah, reflectors. I mean, there's some nice refractors out there, but none of the world's major observatories use a refractor, because you can make reflectors much larger for much cheaper. Yes?
So does the, is the universe is the universe, the same way that a star, is like fighting like gravity and pressure? Does the universe, does the universe do the same thing?
So there certainly is gravity playing a major role in the universe. In other words, the shape of space is determined by the influence of gravity. Pressure doesn't really play a major role in the universe as a whole. If you're talking about ordinary kind of gas pressure or whatever, the universe is not like a balance between pressure and gravity or anything like that. It turns out, however, and we don't have time to go into this, but it turns out that there's a different way in which gravity and pressure interplay in our universe, and that is that if dark energy is what we think it is, an energy associated with empty space, it actually behaves like what is called negative pressure as opposed to positive pressure. And that negative pressure produces this sort of anti-gravity effect that the dark energy has. But I can't go into that right now. I'd love to, but I'm going to restrain myself. Yeah. But there is a sense, in that sense, then, the expansion of the universe is not a balance between pressure and gravity, but it's kind of it's a competition between kind of ordinary gravity and a negative pressure associated with space. Yes?
Can you go over standard candles?
Sorry, I couldn't hear you.
The standard candles?
Standard candles, yep, so standard candles. It's a fanciful name based on the idea that if you had a candle company that made very standard candles, in other words, it manufactured them all precisely the same way, why you can be confident that every one of its candles burns with exactly the same brightness. That's where the name comes from. What it represents are astronomical objects where we know how bright they are based on some other property that we can determine without having to directly measure the object's luminosity. So a classic example is Cepheid variables, where you have to calibrate standard candles. You have to measure ones that are close enough to you that you can actually determine how far away they are, measure their apparent brightness, use that to figure out what their luminosity is. Once you've calibrated a standard candle using nearby ones, you can use much more distant ones where you can't directly measure the distance, but you can use their known luminosities and the apparent brightness to determine the distance from the inverse square rule. Cepheid variables have a relationship between the period, in other words, how long it takes them to go from brightest to dimmest back to brightest again, and their average luminosity. The longer the period, the higher the luminosity. So if we observe Cepheids, and Cepheids are giant stars that are very luminous, thousands of times more luminous than the sun, so we can observe them in other galaxies. And then the idea is we can observe a Cepheid in another galaxy. It's way too far away to use parallax or anything like that to measure its distance. But if we measure its period of brightness fluctuations, from our calibration from nearby Cepheids, we can say, aha, that Cepheid has a period of thus and so, and therefore its luminosity is, say, 10,000 times the luminosity of the sun. And then you measure its apparent brightness, and you can calculate how far away it is. That's what Hubble did in order to determine that the Andromeda Galaxy is a separate galaxy from our own. And I think is that chapter 20 probably, or not?
Yes.
Yes, okay, right. So here is in fact the period luminosity relation for Cepheid variables. So if you find a Cepheid in another galaxy, you determine that its period is 30 days, brightest to darkest to brightest is every 30 days. It's 10,000 times the sun's luminosity from the plot. And then you can measure how bright it appears to us, to our instruments here on Earth, and you can say, for a star 10,000 times the luminosity of the sun to look this brightness, it has to be this many light years away, using the inverse square rule. And that's the key, is that standard candles are bright astronomical objects where we have some way of knowing how luminous they are independently of measuring their distance, so that we can use the luminosity and their apparent brightness to infer their distance. So Cepheid variables were one important standard candle that we encountered. The other, and there are others, but for us the two most important these days are Cepheid variables and white dwarf supernovae. White dwarf supernovae especially are spectacularly luminous, way more luminous than Cepheids. And because they all result from a similar explosion of a white dwarf, they're all about the same luminosity. They all reach a peak brightness of about 1 billion times more luminous than the sun. That's bright enough that with telescopes we can see them in galaxies that are billions of light years away. And so observing white dwarf supernovae in very distant galaxies and determining how far away those galaxies were and comparing it to their measured redshifts allowed us to see how Hubble's constant, quote unquote, has been changing with time, because Hubble's constant, remember, is constant in space but not constant in time. That's what told us that the universe is accelerating, because very distant white dwarf supernovae are systematically dimmer than we would have expected if the universe had been slowing down its expansion. And the explanation is that the expansion of the universe has been speeding up so that those white dwarfs are further away from us than we would have expected, making them look dimmer to us than we would have expected in a slowing down universe instead of a speeding up universe. Anybody want to follow up with that? Ask me another question.
with the timeline of the early universe, like when we're talking about the Planck era, the gut era, and so on.
Yeah. Mhm.
Do you want us to know like the specific times, like that the Planck era is from 0 to 10 to the negative 43rd?
I only sort of know that myself. I love it.
Okay.
That's a hint. Yeah, no, you don't have to memorize it. No, not those times like that. I mean, I roughly know it, but I don't exactly know it because I know where to look. You know, I do. You ought to know that 380,000 years was that special time when recombination happened. That's kind of big, 380,000 years old for the age of the universe then. And Big Bang nucleosynthesis, the universe, that's like the first 5 minutes. Beyond that, no. Beyond that, it'd be more like, okay, here's a figure. Tell me what it means, via multiple choice. But in other words, interpret this figure or this, blah, 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 and there's multiple choice questions. In particular, I'm talking about that timeline that I think you're probably referring to. In other words, so many chapters. Let's see. You're like, tell me about it, Dr. Harmon. So many chapters.
I think it's 22.
Is it 22? Yeah. Let's see. And then I've got the tabs are too small for me to even read it, so I'll just pull up 22, and it might be the second tab it's in or something like that. But I'm thinking in terms of, yeah, it's 22, yeah. And it's this business here, all this stuff. But you don't have to memorize all that. It would be more like via multiple choice question, tell me what this means. That kind of thing. Interpret. Yes.
Has anyone asked about baryons yet?
Wait, what's that?
Has anyone asked about the?
Nobody has asked about baryons yet. No.
Yeah, I wanna ask that.
What do you want to know about baryons?
So it says what baryons are and what is meant by baryon in that.
Yeah, so baryons are particles that contain 3 quarks. And the most common baryons in the universe are the proton and the neutron. There are these exotic particles that contain other quarks besides up and down quarks. But the only stable, no, neutrons aren't stable by themselves. But anyway, the only abundant baryons in the universe are protons and neutrons. And I like protons and neutrons because, I'm a lot of what I'm made of is made of protons and neutrons. And everybody I love is made of protons and neutrons and electrons. And every planet I enjoy, baryonic matter is protons, neutrons, electrons, the kind of matter that we're made of, in other words. So electrons are not baryons, but we still lump them in with baryonic matter because they orbit nuclei that are made of protons and neutrons. So baryonic matter is the quote-unquote ordinary matter in the universe, which is a bad name because it's in the minority. So it should really be like the extraordinary matter, not the ordinary matter. But on the other hand, it's what we're made of, so we think of it as ordinary matter. Yes?
What forces are thought to have operated during the Planck, gut, and electroweak era?
Yeah, so during the Planck era is when we think that all 4 forces acted as a single force. So in other words, just one force. And we call that fancifully the toe for theory of everything, because anatomy, why not? So, and then after that, what's the first force to split off?
Gravity.
Gravity splits off first, and so then you would have a combined, still the three kind of subatomic, well, not sub, I shouldn't say, the three other forces, electromagnetism and the weak force and gravity, stop it. Electromagnetism, the weak force, and the strong force would all be together. And so a theory that unites, we don't have a successful theory yet, but a theory that united successfully the strong nuclear force, the weak nuclear force, and the electromagnetic force, we call that a GUT, a grand unified theory, because anatomy, we just have to name things after ourselves somehow. So there'd be, in the GUT era, is the gut force and gravity, or the two forces. Then the strong force would split off, while the electromagnetic and weak forces would still be unified. And the unified electromagnetic and weak force is called, creatively enough, the electroweak force. And so the electroweak era would be when there were three forces: the strong nuclear force, the electroweak force, and gravity. And then after that, the electromagnetic and weak forces split off, and then there's just, then we're back, then we would be what we've had ever since, four forces operating within the universe, and that would take place at about 1/10 billionth of a second after the Big Bang. So the universe did not spend very long having forces unified with one another. When it got to the ripe old age of 1/10 billionth of a second, we got to the point where there were four forces operating separately from one another. Yes?
Can you go to the lighthouse model for the pulsars?
Yep, so that's the idea, that there are beams of radiation coming out of the magnetic poles of a pulsar. It's a rapidly spinning neutron star. Too many tabs, I'm just going to start closing them. And those beams of radiation would sweep around similarly to the way that the beams of a lighthouse do. And every time a beam passes by our line of sight, years later, when the light finally reaches us, we would see a flash, from the pulsar. I just can't help myself. A flash, from the pulsar. And normally we see them in radio waves. Did I just completely close everything? Okay. Yeah, I don't think I've ever had an open this one yet. The bizarre stellar graveyard. So, that's the basic idea, is that when we see flashes of radio waves from pulsars, sometimes visible light and even X-rays for some of them, it's like the beams of a lighthouse. In other words, a lighthouse beam doesn't flash because the light itself is turning on and off. It's just because the beams are sweeping around and we see beep, beep every time a beam goes past us. Similarly with a neutron star, the Crab Nebula, one of the most famous ones, we actually see both beams, and so we see two flashes per rotation. Most of them, though, the beams are at an angle to the rotation axis other than like 90 degrees. And so as a result of that, we only see one of the beams going past Earth, and so we see one flash per rotation.